Alright, time for another draft physics video presentation. Featuring me, your presenter. Anyway, so comments, I guess. See where we go. I still want to do some more of that World Science Fair video with because it's just too silly. I don't know if we'll get to that though. So anyway, this guy called Dot Null, who I did block just because he's always off the subject and it's whatever. But anyway, he posted a link to a, I believe you'll find this interesting, Gary. Thank you for annotating the link anyway. I could be wrong. You should have just said what it's about, frankly. So it's one of these stupid popular videos where he's making a sound lens out of different gases, you know, in balloons. And it's nothing like a lens. It doesn't collect more sound. It doesn't really amplify the sound. It really is a big failure, a big waste of time. And we already have a simple way to amplify sound. It's sort of like the light argument. You can make a telescope easier by just creating a reflective mirror, okay, and reflecting the image, you know, equidistant kind of argument. That if you put your focus, you know, some distance, then all of these lines are the same length. And so all the light you collect from all these locations, the light comes in this way, it'll all reflect, and you can take a lot of photons and collect a lot of photons with a mirror. And it works. And you can do the same thing with sound. You can collect a bunch of sound with a parabola and then, you know, collect it all in one point, you know, the reflections. And that works so well that no one would bother trying to make a mechanical thick lens idea to bend sound into a focus, because it just won't work that well. I mean, I think theoretically they could just come up with a physical material and just make it at different thicknesses, and, you know, as long as it transmits sound well, they could collect the sounds and, you know, bend them to a focus. But who cares, because this already works so well. Who would bother wasting their time with doing it the hard way? So not very relevant actually. And so blah 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 blah. Thank you for wasting some of my time. Yeah. So it's just a life on Earth. You're going to have to waste some time. All right, this Alec Griffith. This one's okay. I wanted to share this article to you about the LIGO mirrors work. Kind of cool technology. It just makes the whole story even more preposterous, which is the funny part. So yeah, they say they can't. Okay, so I'll try to, you know, sum it up. They say they can't use a regular silver mirror because their laser is so intense that it would melt it, right? So the first question you got to ask is, why do they need an intense laser, right? I mean, the experiment isn't, it's like they're shooting light through an evacuated tube. I mean, it's a vacuum, all right? So the light certainly isn't degrading because there's a bunch of fog in there or something else dispersing the light. So we know that the light's going to be pretty well, as much light as you shoot is going to get to this other side pretty reliably. So you're not going to have any losses there. And technically, your mirror, now they're saying it's 90, you know, 0.99999% of the light reflects off their mirror. Well, if it's reflecting that percentage of the light, again, why do you need such a strong beam? You know, I mean, why such a volume of light do you have to bounce off this mirror 1,600 times if you're losing just this tiny amount? What, you know, who cares? So the real game is they're shooting a big, giant, intense amount of light because, again, they're playing this little tiny photon game. So they're presuming, okay, that the arc line, you know, where something, you know, you go from destructive to constructive, they're assuming that line is so perfect, you know, that the number of photons you're getting, right? So when there's constructive, you get, let's say, 100% of the photons, and you get 0% down here. And their assumption is that this line is so perfect, you know, so perfect a line, okay, that, you know, they can collect a tiny one little, well, one little tiny 1 million of the 1 millionth of a photon. I mean, they can send a billion photons, right, or trilgazillion or whatever it would be, right, and they'll collect one of that huge giant number, and then they'll say, that's one notch on their little ruler, right? So this would be if you got 1 billion photons here, right, and this would be where you got just one photon back, at this at the signal, and that would be some measure of your constructive to destructive interference. Now, if you actually watched any of those interferometer kind of videos, you would see that that light doesn't blink that way. That it really does go, it doesn't like go gradually on and then gradually off. It doesn't get gradually brighter and then gradually darker. It blinks. I mean, it really does go kind of like, it's on, oh no, it's off, no, it's on, no, it's off. So, I don't think they have any realistic hope of doing any of that nonsense, because it isn't doing some perfect line from 0 to a billion. But anyway, so that's why there's so many photons, I guess, they're sending. The only thing I can deduce is that that's why they're saying they can measure 1/10 billionth of the width of a proton, is because they're assuming that they've measured something by detecting a tiny fraction of the signal. All right, but it doesn't fix the fundamental problem. So here's what I mean, I was saying it was bad, like if they were, if the length of their beams were getting noised, they were getting bad readings because the beam went, I was arguing just like 5 atoms worth or 10 atoms worth, right, which would be just 5 or 10 nanometers worth of irregularity, just 5 or 10 nanometers worth of change. They're conceding, okay, because they're using a mirror with layers, 36 layers of film. All right, so this is back to the thin film kind of thing. Okay, so they got 36 layers, and they want to increase it to like 50. And again, and they're not using even visible light. They're using light at 1,000 nanometers. Okay, so they're using infrared laser for some inexplicable reason. So again, now we have these numbers. The wavelength is getting bigger and bigger, which means your fluctuation is spreading over more space. The polarization is larger, and it's less and less precise. You're not using as fine a light as you could use. The higher the frequency, the more information you can get back out of the frequency. The more resolution you have. The higher this number, the less resolution. Okay, that's why you can't see very good with infrared, is because of this wavelength problem and the polarization problem that goes with it. It loses resolution. So you want something that's got higher resolution. So I don't know why they're not using some kind of ultraviolet light laser. But anyway, regardless. So these layers are designed to create in-phase reflections. So they're basically designed to be 1,000 nanometers, okay, in thickness, the same wavelength. So you get perfect in-phase reflections. So no matter where you reflect, these are always in-phase reflections. But the problem is these distances are going to be gigantic. If you're hitting the 36th layer, that's 36,000 nanometers, okay, of irregularity you've thrown into 3,600. No, 36,000. It's 36,000 nanometers worth of distance difference between the bit of the photon reflecting here and the bit that reflects from here. It's 3,600 nanometers different in space. It's a different place in space. That means this is 3,600 amount of noise for every single reflection is potentially 3,600 nanometers off. How can they be comparing the distance of these two beams when every time the beam hits the mirror, it's a number of wavelengths in change in distance? How can that possibly make any sense? So their mirror is much worse than I was conceding. I was conceding they had the best. See, all they care about is getting the photon back, because then they can do their, well, I sent a billion photons and I got one back kind of argument, because of this dependency on this line being perfectly linear, which you can see in the pattern that it's not. It's not a gradually on, gradually off pattern. Especially this kind of interference pattern. The bullseye pattern is even more obviously not gradually on, gradually off, gradually on, gradually off. It's even more obvious than the two-slit experiment that it's not going gradually on, gradually off, gradually on. No, it's a bright, and then it's a off, and then it's a bright, and it's an off. I mean, it's glaringly not gradual. But anyway, so again, so the critics, the defenders of the faith, your religion of woo, you know, how do you explain, how do you measure 1/10,000th of the width of a photon with a ruler that is stretching and contracting by 3,600 nanometers 1,600 times? I mean, if I go 1,600 times 3,600, I'm going to get like 4 feet. It's going to be a really big difference, a really big pile of noise. I mean, obviously the distance is going to be, this one could have gone this far and this one could have gone this far. The two beams are going to be screwing up by a matter of, I mean, we're into real inches here. So how do you account for how you measure 1/10,000th of the width of a proton with rulers that are stretching and contracting essentially, with beams that go in and out of a substance of variable amount, and the varying amount is billions of times more than the width of a proton? I mean, trillions of times more than the width of a proton. How can that make sense? I mean, maybe there's some really cool trick to it, but I'm just saying it seems like it almost has to be a miracle trick. So explain to me, please. Provide me some documentation explaining how your rulers can be this noise prone, and yet you're saying you can see something so fine. It's like saying you can see a microbe, you know, through 100 feet of fog. How can you do that? All right. Incredible claims, very uncredible evidence. So anyway, thanks for the link, as you know, because it does pretty much demonstrate that it's much worse than I thought. Anyway. So, till the next. See, I didn't even get into what those little layers do. Besides the fact that those layers are wavelengths of light thick, and they're conceding that some of the photons are hitting the 36th layer. You know, some of the bits of the photon. So they even talk about the photon like it has bits, like some piece of the photon. See, pieces of the photon hit different layers. They even say those kind of words, which is my theory. Obviously, it's not a wave theory. Waves don't do that. That's why Feynman would say a wave doesn't do that. But anyway, where was I going with this? So you got the argument, the thickness. Yes, so you got that huge amount of thickness built into it, but those layers also create internal reflections, which means this is another source. Their mirror is another source of the bullseye pattern. It's going to end up creating those on and off stripes, just like two pieces of glass smashed against each other with dust in between will do it. So it's going to be, there's going to be internal reflections between those thin layers. That's called thin film diffraction, or reflections, or refraction. And those little vibrations, you know, the little internal reflections are what ends up creating the bullseye pattern. So we have another source of it. Anyway, certainly we're not going to get back what you put into that mirror. Okay, you're going to get something different than what went in. Whatever image goes in, you're going to get back an image that's compositely different. Now, you might be able not to see the difference without a really fine microscope, but there is a difference in what you're getting back out. So anyway, yeah, enough said. Yeah, on that. Interesting article, so, yeah, but complete bullshit. You know, I could just read some. See, there's an image of it. See all these layers. So they got whatever this is, tenica, and then silica, and then silica. You know, and again, these layers are designed to be wavelength 6, which is 1,000 nanometers, which is 2,000 atoms. And it's more than 2,000 because I wasn't counting the space between the atoms. So you're talking about an awful lot of atoms that you're traveling through variably, and yet you're going to say you're going to measure a subatomic particle, something much smaller than the atom, with something that changes, that varies by thousands of atoms in its length. So a ruler that moves thousands of atoms is going to measure something that's 1,000,000 times smaller than an atom. I don't think so. I just don't think there's any logical reasoning that can fix that. So, you know, of course, they just interviewed people who work at LIGO, so nobody else involved in this kind of technology was, their opinion was not requested. So look at the size of this thing. Now that is because of that's how much their laser is spreading. So let's say they hit, you know, 3/4 of this mirror. That's how big their beam ends up being. Pretty damn big. Which is obviously another problem when you're talking about single photons and you know, measuring the distance of 2 photons that went 2 different paths. Yeah, now it doesn't seem very likely that that's what you're measuring. So anyway, yeah, so they don't raise any of these problems in the article, so it's not going to give any information about any of that stuff. But anyway, just it gets worse and more. Like I said, the more details you know about these experiments, the more they're doubtable. The more their theory becomes incongruent. And it's true about the entanglement and everything else. And you people just keep trusting these people. Again, they still can't explain the 2-slit experiment properly. And this guy's an example. You know, this Eric's electron. So what a douche. But anyway, you know, a guy I have in the past solicited conversation from and got no response. But anyway, the probability is going to be straightforward. And then he says, I don't know exactly in what context I said that, but obviously we watch something and we can figure out the probability. So we can flip a coin and figure it out by watching it. We can spin a roulette wheel. We can learn the probabilities, and once you figure them out, they're pretty rigid. You can't break the rules. See, these people actually believe that if I set up a dice rolling experiment and I limit the number of variables, you know, which you could do, even randomizing lottery balls. We know that in the past they had certain variables that weren't complex enough, and so the balls would always roll into the device with the 1 first and the you know, the last number last, and it changed the outcomes. So there was a way of gaming the system because certain numbers did come up more and certain numbers did come up less because they didn't quite randomize it enough. That is, they didn't create enough variables to make it impossible for the variables to match. And we know that's all that makes the difference. So when you roll dice, we know that it's the number of interactions that makes it that makes the probability rigid. Because you've gone beyond any mechanism that can ever create the same pattern repeatedly, or that any pattern is simple enough. But I can reduce the experiment, right? I can reduce flipping a coin to, you know, if I put a little enough energy, I'll just flip the coin once and it'll land exactly opposite the face I'm showing, right? I can flip it and just make it flip once, and we know that the probability will be that it'll always be the same outcome on 100%. We'll never get a tail, or we'll never get a head, depending. And so I can take variables out of a system. So if it was a dice table, I could take variables out by just saying, okay, you don't hit walls, because walls create all kinds of variation. So the more variation I take out, the more and more it'll become a system where if I throw the dice with, snake eyes, I can make sure I get boxcars at the end, Not make sure, but I can vastly increase the likelihood by creating as few variables as possible to screw it up. But anyway, but probabilities are rigid in the sense that once a system has variation in it, just like a curved space, and the rule is, there's a line going to come down. Now the rule is this line is completely randomized. That is, it went through some filtering process, and it does turn out that this is 10%, 10%, 10%, 10%, 10%, they're all equal, and I could just have them hit around surface, and I have a guaranteed certain probability of outcomes. The outcomes are going to be completely proportional to the internal circumstances and the variables provided, and so I'll end up with the same probabilities out here of outcomes. And that's the nature of probability. But each event is an inevitability. Each event is a real event. The thing hits a real surface. There's real angles. There's real outcomes. And there's this idea that somehow there's like I said, somehow the penny that I'm flipping is going to break those rules. So if I just give it one little bit of energy to flip it once, that somehow it's going to do a quantum thing and decide to flip twice. It can't flip twice. Just as this thing can't hit this point and go this way. That can't happen. If you want to go this way, then you have to hit somewhere on the surface that makes that way the possibility. But it can't happen. There's rules. The physical rules are obeyed, and this is just such a nonsense to be even indulging in this conversation about how there's some sort of irregularity built into something, when we know we can make systems that don't have any irregularity in them, because we just remove the variables. All right, anyway, probabilities aren't straightforward, though. Yes, they are. So, and inevitabilities are even more straightforward. The fact is, they're all inevitabilities, and the variables are definable. Your ability to grasp quantum mechanics, such as the double-slit experiment, which is, I just did a video debunking it entirely, and he's not going to respond to that video here, right? Which you're free to replicate. Yeah, I'm free to replicate it. What I'm even more free to do is actually come up with a theory that predicts more with less information. So it wins. I mean, even if we say it predicts more with the same amount of information, it predicts more. I can tell you more about what the outcome is going to do than they can. I can tell you that you just move the two outside surfaces, you move those, and you'll change how big the little bars are. And if you move the two interior surfaces, you'll change how big, where the little dark spots will be. The two, the envelope pattern. Where do they tell you that? Oh, that's right, nowhere. And I'll tell you that the point sources are the surfaces. There is no, the two waves drawn by Young. Again, Young's experiment was in 1801, so you can say, well, Young could make these stupid mistakes. But obviously, by the time Einstein and Bohr and all those assholes were talking about this, they should have known better. And the simple truth is, this drawing does not work. Okay, if I make two waves here and I do this little drawing of the waves, so if I make these the point sources in the sense that these are the waves diverging, and I use that mechanics, I will not accurately predict the pattern, because this is going to be the pattern, right? This is going to be the pattern, and then there'll be a big blank spot there, and then the pattern will start again. All right, oh, you can't see the big blank spot. Oh, that's disappointing. Yeah, that's a error on my part. Sorry. Well, I just moved the camera, right? Yeah, that's what I'll do. I'll move the camera over a little. There. Okay, so now you can see it. All right. So this is the real pattern, and we know that we can kill this part of the pattern if we make these slits so infinitesimally small that there's no increased distance. You know what I'm saying? So when you add the distance between these, the impediment, and the distance between the widest distance, the narrowest distance and the widest distance have so little difference that the two patterns end up being superimposed on each other, and you don't get this and this. But any slit width that's more than infinitesimally small will give you this pattern. This is the pattern created. And Young's waves can't do that. What can do that is scatter from these point sources. So point sources here can't create the pattern. Wave centers don't work. The math is wrong. It doesn't predict the pattern. This does predict the pattern. 4 point sources at the surfaces. That math works. And obviously that's not going to be where the waves are going to be. There's no rational reason to say the wave is there and then the wave is there, you know, halfway on the halfway over the material. Nobody thinks waves are created that way. So you're stuck. You're done. Your wave theory doesn't work. It doesn't perfectly predict. It doesn't do any of the hype and crap that it's been propagandized to be. And my simple explanation works fine. It perfectly explains the bars and it explains the envelope. Deal with that, Eric. I always hated Eric as a name. Always hated Eric's. Alright, anyway. Which you're free to replicate. See, so they talk about it as if, okay, if you do the experiment, it'll come out their way. No, it doesn't. And that's the truth. This pattern's made, not Young's pattern. Retard. Isn't evidence, it isn't accurate. So this is so vague and nothing, right? He has stated nothing. He just said, you're wrong, because I say so. Fuck you. Well, anyway, so Dave says, prove it. Yeah. And then Dave says, exactly. Okay, you glob off and put the entire onus of an experiment onto a guy that has released hundreds of videos on the subject, which you haven't watched, clearly. Yeah, exactly. He has no understanding of the theory, and yet he talks this shit. So let's see what he says. Okay, Dave, prove that. Okay, that probabilities aren't straightforward, question mark. Well, yeah, first prove you understand what the word probability means. Because obviously it's supposed to mean something. Okay, I mean, glass goes through certain layers, right? You polish glass, it goes from 16% to 15 to 14 to 13 to 12, 11, 10, 9. It doesn't go 16, 8, 4, 9. It's rigid, the probabilities. Okay, it's in the definition, probabilities are probable. And what does that mean? It doesn't mean anything. It, you know, again, the variables causing the probabilities are rigid. They're real in their variation. Okay, meaning not straightforward. So again, he says not straightforward. What does straightforward mean? It doesn't mean anything in this context. I'm not saying one event happens. I'm not saying you flip the coin and it just comes up heads all the time, right? That's, you know, we're saying there's a probability. Well, what's the probability based on? Well, it's based on rigid mechanics. Okay. And the double slit experiment has been replicated many times before. So this, you know, again, these idiots are so fucking stupid. You know, they talk as if the experiment is self-explanatory, or that it's just this simple, yeah, two waves interfere and you just get bars. No, this is what you get. You get this on-off thing, this complex pattern. There's nothing straightforward about that, and there's nothing straightforward to their explanation of those two patterns. Why don't you show me the video where they deal with those two patterns? Anyway, it's up to you and the person in the video to prove the findings aren't legitimate. And I've done that. I've demonstrated. I've drawn your pictures and explained how they don't work. It's your obligation to explain how it does work. How does these two waves create this pattern? Show how you can show how two waves coming out of these two slits create this pattern with these breaks in it. Explain how two waves do that, because they can't do that. They can't do this and this at the same time. They can't do it. There's no way to draw it. There's no way to mechanically make it make sense. It can't create the pattern. You keep saying, yes, it does. It's most proven math in the history of mankind. No, it isn't. That's all hype and bullshit. So let's go to this moron's channel. I've been there before, and he had videos about, you know, his whatever, high school politics or college politics or whatever. Says he's being discriminated against and whatnot. All right. 5 months ago. So this one's 3 major facts about... Oh, Jesus. I wonder if he's wrong about those. Here's some major facts about the virus, okay? The only thing that makes this virus any different than any other flu virus, okay, is the fact that we're all not immune. And that's it. I mean, its likelihood to kill you is nonsense, because obviously, you know, the statistics they do for the regular flu, they just approximate. Nobody tests for the regular flu with any kind of regularity, so they never know how many people actually got the flu. Okay, they're just made up numbers. In this case, the only deaths they're counting are people they tested whether they died of the flu or not. So I mean, it's clearly these numbers look more dangerous, okay, but it's only because we have no real number for how many people actually have this stupid virus and didn't know they had it. So there's a ton of people that have gotten it and not realized they had it and have never been tested. So there's a lot more survivors than the statistics indicate. Probably twice as many, which means it's exactly the same mortality rate as a regular flu. And who's dying? Yes, it's old, diseased, crippled people. That's the only people it's killing in huge numbers. By huge imbalance, it's killing the old. I mean, so come on. I'm not saying the fact that nobody is immune is a real hard piece of bad news. And so obviously you have to slow down so everybody doesn't catch it in the same week, and you know, that's a real crisis because more people will die, obviously. But the rest of the hype is just hype. Okay. And so then he's doing some kind of transphobic crap about fucking Harry Potter bullshit. College students versus racist professor. So yeah, this is just, what the fuck does this have to do with physics? Oh, absolutely nothing. So, your channel sucks. Yes, a physics channel, it really sucks. Let's see. Is there a physics video to be found? Now, these are all the, you know, I couldn't find a decent physics video anywhere here, so. A is for atom. Oh, that's probably really interesting. You know, it's a 1953 film, which are, you know, those are nice to watch, actually. Somebody will watch it just because some of those are pretty good. Fake news, chemtrail fake news debunk. So he's doing debunking videos of truth or nuttery. Oh, what a challenge. I need all this crap. Who wrote the musical score?
The atomic age was born. There is no denying that since that moment, the shadow of the atom bomb has been across all our lives. All men of goodwill earnestly hope that a realistic control of atomic weapons can and will be achieved. Meanwhile, good sense...
Yeah, well, whatever. Yes, we'll assure each other's destruction. That'll be the solution.
...power at man's command. And where was it science found that giant? In the atom, a particle so infinitely small that it takes over 100 billion atoms to make up the head of a pin. Just as other millions and quadrillions of atoms are the tiny building blocks.
So again, just realize that, and then light is relatively covers a whole bunch of atoms. One single photon somehow is covering in space. Its polarization is thousands of atoms across. And somehow we're supposed to believe that the photon is interacting with one single electron, and one single electron creates a new photon. No chance.
Which make up everything in the world. Ships, and shoes, and sealing wax, and cabbages, and
Nazis, and blah, 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 blah.
Although no one has ever seen an atom, scientists have learned a great deal about how they behave. And there are widely accepted theories as to what they're like.
All right, so widely accepted by the popery, okay, by a collection of people that are getting paid to, be part of a club and tell the dumb heathens what the truth is. So this really is just like a religion, right? These are just your bishops and your whatever they're called. And, they're just doing the propagandizing to the ignorant masses.
Let's start by meeting a leading authority on the subject, Dr. Atom. Now, observing the professor himself, we can see that his structure resembles, in many ways, something almost as vast as the atom is small. The solar system. And there are certain similarities.
Here says them, right? So, really there aren't any. Gravity is not really the same thing as charge in terms of it's not dealing with the real trick. It's purple, okay? The solar system is all in purple, and the atom is blue and red, and that's sort of a good analogy, I think. Lots of blues and reds bouncing around atoms. All purple around, the Earth and the Sun.
This is the center with electrons in surrounding orbits.
So that orbital model was always flawed in terms of figuring out where did it get this momentum? How could the momentums all be the same for these electrons? They'd have to have the same velocity, right? Orbits are dependent on velocity. So none of that makes any sense. How do you get the precise velocity for the orbit? Again, in solar systems, it all turns into ellipses, which would just mean these electrons would be having all kinds of chaos with each other because their ellipses means, they would be gravitationally influencing each other very differently, and each time they spun around, and so they're going to be wobbling everybody else's orbits even more. It made, lots of reasons to know, it's got to be something else holding them atoms together. I would argue that it's something else. And we know there's only 100 of these configurations. You can only arrange these 100 different ways, with some slight variations, adding an electron or something. But I mean, the nucleuses, right? You've only got 100 of these things that really work as arrangements that hold together, that are durable. And that's it. I mean, it's a tiny number of geometric arrangements that work. And if I change that geometry, it falls apart, it breaks down. My argument would be that makes sense when you think about the geometry of magnets being placed in positions, with their poles facing each other and such. Like magnets between two pieces of glass so they can't flip. And the fact is you can move them around and do different things. You push one of them, all the other ones move. Lots of things are possible. And if you do that in 3 dimensions, you realize, the magnetic model would have been the rational model. To realize that these electrons are repelling each other, and then they're attracted to this center, and they're just frozen in these positions because this electron can't move towards the protons without it moving closer to these electrons. And that's why it doesn't move. That's why it's stuck there. And that when they share an electron, they literally share this electron. It's in the same position, and the two atoms are bound to a single electron or to two electrons, in their bond, and they're literally sharing it. That model is so much better.
But whereas the planet's movement, trons, is slightly different, there are other differences too. Hey, hold it! Thank you. Now, the solar system...
And so now the modern woo is, it's an electron that doesn't know where it is. It's superimposed over 4 million different locations in some kind of swirly blob. It's just such horseshit.
Together is electrical. The electron...
No, it's magnetic. Yeah. These are the monopoles of magnetism. Surprise, surprise.
Which are negative are attracted by the protons, which are positive, and vice versa. But here in the nucleus...
So, see, totally eliminated from that analogy. Could have, see, so you have net protons. You have net positive because the neutrons are positive and negative, so they cancel out. So you have a net number of positive charges, and the electron is negative, and therefore it's attracted to the nucleus because there's more positive there than there is negative, more attraction than repulsion. But no one says nothing. They don't even show these electrons hate each other, absolutely hate each other. Okay, so they show this attraction, but they don't show this repulsion, and they know it has to be there. So why don't they show that too?
Are other particles with no electrical charge called neutrons.
So again, it's not that they don't have no charge, it's that they have both charges. They're doing the purple thing. So the neutrons are doing the purple thing, the protons are doing the red thing, and the electrons are doing the blue thing. And blue reflects blue, and red reflects red, and red gets deflected by blue, and blue gets deflected by red.
Very important characters too, as we shall see. And equally important when it comes to atomic energy is what scientists call the atom's binding force. It's a kind of cosmic glue holding the nucleus together.
Right. So what's really holding it together is the neutrons, because the neutrons have an electron. So it's like an electron, then a proton, then an electron. A proton, electron, proton. And that means all the positive repulsion gets mitigated by the electron, which shoots it out sideways, and so now the two protons can get very, very close to each other. So you don't need any binding force. The binding force is an absence of force, the disposition of force. You remove the little bits bouncing between the protons, and then the protons won't repel anymore.
This then is a single atom. But certain.
So this is, they tell you this story like there couldn't be any other story. They say like, oh well, we're 30% sure this is right, or this is 60%. They don't even give you any kind of notion of why they think this must be the right answer. And they certainly don't test you with any kind of, well, it could be magnetic and I could do this, and just understand how magnetism would do the same thing. They don't even try an opposing model. So they just make it sound like, oh yeah, this is what we figured out, this is the truth. And again, now they've changed this, right? Because now they're conceding, well, these orbits would degrade and all this other crap. Well, they obviously, I don't think they would. But obviously they would with the tension between the electrons. So as soon as you added more than one electron into the system, the solar system would break down fairly rapidly.
Not all atoms are alike. There are in nature more than 90 basic elements, which is science term for families of atoms.
So it's kind of silly to say families of atoms. We're really talking about a geometry, a basic geometry, a number of little things arranged in a certain geometry that is stable, that survives. And we know that there's only 75 or so that are really stable, and the rest end up being, they're radioactive in some point where they're falling apart at some rate.
Scientists, the atoms of the individual atom families, or elements, are identified by number. That is, the number of protons or positive charges in their nucleus. And they vary all the way from hydrogen, which has just 1 proton, to oxygen with 8 protons, to gold, he's rich with 79, finally on to the heaviest of all natural elements, uranium with 92 protons.
Well, obviously they found some heavier stuff, but anyway, moving on.
Now, within each element, or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes. Some elements, tin for instance, have a great many isotopes. Others, like aluminum, are lone wolves with just 1. Now, most atoms of most elements are content with their lot in life. We speak of them as being stable, but others are...
So again, it's really just, like I said, you can understand hexagons and then octagons and hexagons and trexagons. You can understand that you can only do certain things, and once you combine, you go from 5 to 6, you go from an odd number to an even number, that you'll break down some kind of system that you were using that configuration for. So you can sort of understand that certain shapes will work, certain shapes won't work. You can only mix certain squares and circles in an arrangement where it stays stable in 3 dimensions.
Busy day and night, being what science calls radioactive. Like radium, throwing off powerful rays along with some of its neutrons.
So the idea of radioactivity, again, is another interesting subject, which, you know, there's just no conversation about any of these elemental functions and what might be causing them or anything. So I'll do a little bit on that subject, just because, you know, I never thought about it either, because they don't think about it, so they don't encourage you thinking about it. I thought about it in the sense that you can have different theories, okay, about why it happens, right? You can theorize that the thing itself is made in a sun. So you would have to theorize that if that's so, then every atom of uranium would have to come from a different location, you know, because it would have to have a different age. If it's decaying at a certain rate and there's no consistency in the decay, that is, it's, you know, the amount decaying, it doesn't seem to be on a schedule like they were all created within the same 100 years or something, every atom. So the atoms would have to come from all kinds of different places in the universe, made at all kinds of different times, and that gets kind of hard to imagine, right? That all of the uranium came from a different location, like every single atom came from a different place. That's hard to believe, or a different supernova or whatever. So this idea that it's internally breaking down, that is, it has some sort of system, you know, it's a clock, and there's a tiny irregularity, and every 10,000 years that little irregularity, you know, all the irregularities inside, all the little timing cycles of all the little things going on inside of it, all line up, and then the whole thing falls apart because of that alignment. It doesn't seem very likely to me that that's the system that causes decay. So what I thought of when thinking about it is that decay is just that the atom is fine, you know, it's stable, and what it is that the environment, okay, can do something every now and then. Some event can happen, probabilistically, that requires a perfect storm. So when the perfect storm shows up, boom, the thing falls apart. Now that makes sense, because you can sort of understand that, okay, why would this stuff decay quicker if I compress it? That is, I put more of it together, I'll increase the speed at which these atoms decay. So if I put a whole bunch of uranium in a box, and take out all the other atoms, I can increase the decay rate. That's essentially how nuclear power plants regulate how they take advantage of uranium's capacity to decay, is they increase the rate at which it decays. So by consolidating it. So I would argue that the real game is that it is sort of like a Death Star, that the uranium is stable. If you keep it in a certain environment, it can just stay in that environment. And all the other ones are being affected the same way. And what really happens is the environment actually produces a circumstance where, say, a cosmic ray hits and another cosmic ray hits at exactly the same point and exactly the same time. They both hit, let's say, the center of the nucleus, and then the atom decays. So it requires this little perfect storm to happen. And these cosmic rays are produced when the decay happens. So when it decays, it actually produces more cosmic rays, which increases the likelihood, if there's another uranium atom right here, that it might have one of these perfect storms. And so it decays. And that's the whole chain reaction of destruction, is just on the fact that you create this little perfect storm, and you're more likely to have a perfect storm if I create a bunch of clouds, a bunch of stuff that's going to cause perfect storms. Now this also would explain why, if I give this atom velocity, that is, I send it in a direction, that I make it less likely for the perfect storm to happen. So you can sort of understand that if I move it in a direction, I'm going to make it harder for certain directions to provide. So let's say if I move it very fast this way, I make it almost impossible for another cosmic ray to come in this way. So the number of cosmic rays coming in this way, the way I'm moving, hitting me in the ass, gets reduced to, like 1/10,000th or whatever, some huge number of likelihood of that happening. And so now I've reduced the probability by changing the variables. And so now, because I don't allow this to happen very often, the two of them can't happen very often. So I slow the decay rate down by moving the atom. So you don't need to dilate time. You don't need to change the universe. You don't need to change anything. You just need to understand, if I move one of these Death Stars in a direction, it becomes harder for Luke Skywalker to shoot his little, torpedo in at the same time, Han Solo shoots his little torpedo in from the other side. You can see it'd be a lot harder for them to do that when this thing's moving. And that's all it really has to do with, is that there's some mechanism, some little perfect storm has to happen, and the perfect storm is a lot less likely to happen if you're moving. Okay.
Neutrons and protons, until it actually alters its own nuclear structure and changes to another family, and then to another, until it does.
So that's really not what's happening, right? The atoms, the uranium atoms, aren't sitting here going, I'm losing all kinds of stuff, I'm losing all kinds of stuff. No. They're perfectly fine. It's just that one of them, in a group of 1,000,000 of them, decays. That creates all that noise. Okay, so it's the single atom decaying. And so when one decays, it creates a bunch of dirt, that flies out of the uranium clump. But the rest of the uranium is fine. It's not creating any dirt. So uranium atoms by themselves, individually, don't create any dirt. Only when they're in a collection do you see any dirt, right? I mean, it's only 1 in 10,000 years. If I had an uranium, just a single atom sitting here, it wouldn't be harming me. There wouldn't be any radiation. The single atom either radiates or doesn't radiate. That's it. It either does it all at once, supernova, or no supernova. Suns are fine until they supernova. Uranium atoms are fine until they supernova. So the uranium atom itself is not doing all that jiggly crap.
Does become stable at last. This spontaneous.
So again, they're all stable until they're not. The individual atoms are stable until they become unstable, and that takes a microsecond. So there's no such that they're alive or they're dead. They're never zombies. They're never leaking energy individually. They're only as a collection. Some of them are dying every second. That's it. Nothing more complicated than that.
This changing of elements is called natural transmutation. Its discovery gave men of science an idea. If an atom could change itself, why couldn't man change an atom?
So again, we already know what the change is. The atom breaks and turns into two new atoms and leaves over some extra bits. So you take the car and you make, two golf carts out of it, and you have a lot of extra parts. That kind of thing. Not that complicated. But there is no I'm becoming a golf cart. It happens in a microsecond. It goes from being a car to being two golf carts and extra parts.
Using as bullets the very particles which radium threw off, a noted British scientist bombarded nitrogen and converted it to oxygen. In terms of individual atoms, this is what happened. The radium nucleus threw off an alpha particle consisting of 2 protons and 2 neutrons. One of the protons was absorbed into the nitrogen nucleus, turning it to oxygen. This was artificial transmutation, man changing the elements.
Right, and so with limited ability, we can do these things by exposing atoms to radiation. So just as atoms can be knocked apart, we can also fuse atoms together. But we can't do it on any kind of scale that makes it at all practical. It's a lot more expensive than just digging up the crap.
From that first experiment, others by the thousands followed as scientists devised ever more powerful particle accelerators, commonly called atom smashers, to transmute more and more kinds of atoms. All scientifically important, but hardly world-shaking. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in two. Truly a discovery to change the world. For what had happened when the uranium atom split was a kind of double miracle of science. Half of the miracle...
So again, it's just about speed. The difference between a nuclear reactor that creates heat and the nuclear bomb is just how densely packed the uranium is and how many neutrons you can get free, all right, to break all the other atoms. And the neutron is just a point of energy. It's just a bullet of kind. And that's all. It's really just its momentum is what's doing the damage. And so you're just creating a bunch of that at one place at one time, and that's what causes the explosion, is because you create a lot of heat too fast. And that's why you get a reaction that's different. But it's just a matter of time. It's just how many atoms do you break, how quickly. You break them all quickly, then you get a bomb. Break them slowly, you get, lots of energy.
Concerned that binding force we spoke of before, that kind of cosmic glue which holds the atom's nucleus together.
So again, the only things holding it together is the fact that neutrons, protons and electrons mitigate each other's function. And so I will just draw this simple. This is my explanation. I think it fits the evidence perfectly. It explains magnetism, explains lots of other crap. And so no reason not to believe. It's a better explanation than their wooey explanation of a magical force that they can't describe or explain. So here's the theory. You got these two positively charged particles. We know that at certain distances they start creating a lot of energy. And how do they create the energy? Well, there's actually energy bouncing back and forth between them. So you can understand that if a little thing is bouncing between them at the speed of light, that the closer they get, you're doubling with every halving of the distance, you're doubling the number of impacts, okay, the little ball will have between the two objects. So the closer they get, the more power there is, the more energy there is. So they're thinking, well, that's a tremendous amount of energy it would take for a force on the outside to push these two protons together, because this is multiplying and it can almost go to infinity, right? I mean, you can get them so close that there's so many reflections that it's a tremendous amount of theoretical energy you can create by just pushing electrons to each other. And obviously they call it a strong force because they're saying, well, it must be an awful strong force that's pushing them together. Well, they're not being pushed together, okay, because the proton is a proton and the neutron is actually a proton, okay, with an electron. That's why it's neutral, because it has both. Okay, so this is your proton, over here, and this is your neutron, sorry. So this is the neutron. The collection of this and this equals a neutron. This is your proton, okay. So what happens when these two interact is that all of the energy, the balls that were bouncing back and forth between these protons, are now leaving this way, or leaving this way. And likewise from this one, leaving this way, leaving this way. And all of this energy that would reflect between electrons is also just being leaked out. So no electron energy can reflect. So you have no reflections in here. And so now you have very low pressure here. Low pressure. So you don't need any big force out here to push these two protons together, because there's a vacuum here. And so the vacuum just says any pressure here, any at all here, will push them together, because there's an absence of pushes this way. I've gotten rid of all the pushes this way. So it's not really a strong force, it's an incredibly weak force. But all it is a redirected force. And that's why the whole thing becomes polar, and that's why you have a positive sides over here, and you have negatives over here, and all that kind of crap. It's because the force is redirected. The ping pong balls, the blue ping pong balls and the red ping pong balls go in different directions, and that ruins any of the propulsive energy between the objects. And the same would be true for the electron. So if I put another electron over here, you could understand that these two electrons could get much closer to each other, because now all the force is leaking out of the proton. So that solves it without this mush. You don't have to invent new forces.
We still don't know all about that binding force yet, but we do know it is equivalent to mass. Therefore, we may speak of it as having a kind of weight of its own. Now, the two atoms into which a uranium atom splits...
So they're giving the energy, mass, and weight, which is probably not a good idea, because it's clearly proximity. All I do is move two closer to each other, and I've created pressure between them. I've made the little piece of energy that's trapped between them, the ping pong ball, becomes more energy when it's trapped between two protons. You can see it, and electrons. Same difference. And all I do to increase how much energy there is in the universe, so to speak, is move the two closer to each other. But obviously, to move the two closer to each other, I have to apply a force to do that. But if I can do it without any force, without any added force, if I just remove that ping pong ball.
Also have binding force, but for some reason it takes less of that glue to hold them together, and in the process of fission, a tiny fraction is left over. What happens to it? It explodes as energy, proving Einstein's theory that mass...
So this is kind of silly about what proves what. And it's obviously not a strong force that makes the atom fall apart. It's actually just disrupting the proximity of this. You remove this little electron, right? If I kick this electron out, right? Can't see that, but you can sort of understand that if I've created a nice balanced system that's doing all this mitigating, well, if I kick this electron out of here, I hit it, knock it out, all of a sudden these two protons now are back in business in terms of hating each other. And they're going to very aggressively move away from each other. Very aggressive, because now there's a whole bunch of force in between them. You can see that would be the implication.
And energy are really the same. But we spoke of a double miracle.
So mass and energy really are the same, and because mass really is proximity, right? What gives atoms their mass? Well, it's collecting more little bits of electrons and protons closer together. The more dense the collection, the more energy potential the atom has. So it's kind of obvious equation, right? The more dense the arrangement of electrons and protons to each other, the closer they are in proximity to each other, the more pressure, okay, that exists if you take away the arrangement that's holding them together, the balances. So as soon as you unbalance that system, the amount of energy that's hidden in it is tremendous.
To understand the second one, let's slow down that fission a million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast.
So it just is this disruption, right? And so you're basically just breaking a piece of it. The two pieces will move with energy, so they have to calculate the speed at which those two nuclei move away from each other. They won't be in that form, actually. They'll have to reconsolidate, but whatever, it doesn't really matter. So you can understand where the extra bits fly out is because you've broken the system, and parts of the system won't be recoverable. Some of the pieces will escape. They'll get escape velocity and they'll leave. Just like sort of an asteroid could hit the Earth, a big one, and pieces of the Earth would go into space and never come back again. And then some of the pieces would come back and blah, 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 blah. And so all you're doing is calculating how much of the momentum will leave the Earth.
Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them...
Right, so in 3 is sort of an important number there, that each decay event leaves 3 extra neutrons liberated. And obviously those 3 extra neutrons hit another atom and create 3, and then that 3 creates 3. So obviously for each atom that decays, it will decay to 3 other atoms. And at that rate, you can understand that as long as they're compactly arranged, you have a whole bunch of atoms in as compact a space as possible, you'll understand that those neutrons will likely hit more atoms and they will start all decaying, and you're creating 3 more decay events for every event, and the math goes exponential pretty quickly.
To split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball. With this discovery, at the time the free world faced a war for survival, it was little wonder the first thought was a weapon. But
a war for political correctness in a lot of ways, right? I mean, wars aren't necessarily for survival, they're for something else. But anyway.
How to obtain enough material for even a single bomb? Only a small fraction of natural uranium is the U-235 isotope, which will fission in a chain reaction. And to separate enough U-235 quickly enough seemed all but impossible. But the impossible became reality as industry, labor, science, and the military combined their efforts to build Oak Ridge, where enough U-235 was separated to build the first atomic bomb.
And the idiots were given this, and they made some horrible casual mistakes with it, and a few people died getting irradiated because you couldn't handle this crap, right? You had to lead shield it and all that kind of stuff, and fucked around it all. That densely compact uranium is, just get within 10 feet of it, and you're, for 1 second, and you're dead.
At Hanford, Washington, another impossible project proved possible when a huge plant was built for the mass production of the artificial element plutonium. This process involves what may be called the furnace of atomic energy, the reactor pile. Here is a structure or pile of graphite blocks. In the reactor are placed rods of natural uranium containing both U-235 and U-238. As U-235 begins to fission,
it's just kind of funny that, nuclear power plants aren't, that complicated in terms of the basic mechanism. And even showing the rods going in sideways is sort of retarded, right? Because you want the fail-safe to be that if something goes wrong, the rods fall out. They fall into the container. The I think it is well, they use water. But anyway, they fall into an environment that separates them, not one that consolidates them. And it's just kind of funny that the fail-safes are kind of the opposite way, and it's, those kind of mistakes are just so kind of stupid.
Graphite slows down the free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms. And here's what happens. Remember, we said that U-238 wouldn't support a chain reaction.
So again, the atom is not doing any of that jiggly crap. It's a perfectly peaceful thing until you fuck with it.
However, it will capture neutrons from U-235 fission and start a process which converts the U-238 first to neptunium, then to plutonium. And plutonium will fission in chain reaction. Thus, the reactor itself is a source of atomic fuel. Besides producing plutonium, the nuclear reactor makes possible two very important peacetime uses of atomic energy. Remember that the chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in...
Sometimes they control it, yeah. Sometimes they don't.
Many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight. However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible. While nuclear power...
So it's kind of neat that, in 1953, they still hadn't built a commercial nuclear power plant. That's kind of interesting.
Or in locomotives, submarines...
Well, the neat thing is those little tiny nuclear power plants, right, that are running like aircraft carriers and stuff, they've been pretty reliable. And it's like, why don't they just make a lot of those? Learn how to do it really well and compact and neat and clean, and do a lot of that.
Ships and even very large airplanes.
That seems a little bit implausible, right? I mean, nuclear-powered plane? Yeah, no, I don't think so.
All but revolutionize future transportation on land, sea, and air.
I mean, you could imagine that planes would be unrealistic, just because he just pointed out how, well, you need all this heavy shielding, you gotta, blah, blah, blah. That's a lot of weight. I can't put that in the sky. That would be kind of retarded.
But perhaps the most valuable byproduct of the nation's reactor piles is radioactive isotopes. Research has revealed that many elements not naturally radioactive became so when placed in a nuclear reactor. And these isotopes, working as tracers with such measuring devices as a Geiger counter, became invisible detectives, aiding the cause of science in many different fields. agriculture, isotopes are now used to test such things as the effect of fertilizers on plant growth and the proper
Yummy.
timing for their use, helping to assure bigger and better yields from tomorrow's farms. In industry, isotopes have found literally hundreds of new uses, such as the automatic thickness control of sheet aluminum, saving hundreds of man-hours of labor and assuring accuracy never before possible.
I used to make machines like that that did that detecting work, how thick something was, how transparent, that kind of stuff. Interesting.
In the fields of medicine and biochemistry, isotopes are performing near miracles of diagnosis and discovery.
Right, and so now we can die more than once. It's so much fun dying. So yes, now you can die 8 or 9 times. Yay.
With radioactive sodium, doctors are solving more of the seeming mysteries of heart disease and circulatory disturbances. Radioactive phosphorus has been used to locate tumors in the brain and greatly
And make some more for later. So you can, we'll save you from this disease and give you a few more for you to die of later.
simplify operations for their removal. Iodine-131 finds one of many uses in revealing conditions of the thyroid, and there are many more. New ways of using isotopes are being discovered constantly through the tireless work of modern pioneers.
Not really sciencey, this part of this, the social propaganda. Thank you, General Electric, or whoever the hell was making
In
this.
such fields as chemistry, metallurgy, medicine, and biology.
Plastics are
Truly
fun.
the superpower which man has released from within the atom's heart is not one, but many giants. One is the warrior, the destroyer. Another is the engineer, seeking to provide vast quantities of energy to run the world's machines. Another is the farmer, helping to better feed tomorrow's world. Still another...
Yeah, but that was just kind of funny, right? But yeah, I mean, look, there's a science to it, right? Fine, yes. You can diagnose, plant inefficiency with your radiation, but it's kind of a minor use.
is the healer, helping to diagnose and cure the sick.
With expensive and unpleasant procedures that don't really accomplish anything but buy you more time to sit around going, I don't want to die, I don't want to die. Yeah, okay, we got that part. You're being unrealistic.
And the last is the research worker, working on in the fields of pure science to reveal more of the mysteries of the universe.
Yes, as we make them up. So they are revealing the mysteries with their propaganda silly story, with their giant Jeebus radioactive man. But they might as well just call Ben Space, some sort of giant mover of things. I am the thing that moves the things, force man thing. Might as well. Same difference, a little blob of bent space. Same thing as a cartoon.
But all are within man's power, subject to his command. On man's wisdom, on his firmness in the use of that power, depends now the future of his children and his children's children in the new world of the atomic age.
Whatever. Bullshitocracy. Live by the bullshit. Live for the bullshit. Live in the bullshit. La la. So profound. Little fucking blue ball of bullshit. A little over orchestrated, I would say, right? Doesn't really go with the theme. It should be something like a lot more like sunshine, lollipops, and rainbows. Do 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 do. General Electric is your friend. Instead of this whatever, sort of doom. What's coming next? I'm scared. Anyway, So thanks, Eric, for the little whatever comic relief video. And but otherwise, fuck you and such. Shit for brain. Make a real argument relevant to the arguments I've made, shithead. I didn't say the two-slit experiment doesn't exist. No, that's not my claim, fuckhead. Ugh, God, these people are just so fucking stupid. Anyway, so another video in the can, as they say. I think that's enough for today. And so yeah, maybe more woo. You know, the story of entanglement, told by that stupid green guy and these other frauds. And they don't even get the story right. I mean, it's not even close to correct. You know, they kind of blame Einstein for inventing entanglement. He didn't do that. Okay, he gave you a thought experiment that didn't have any entanglement in it. It's just to demonstrate that your wooey, you have to look at it crap doesn't make any sense, because I can create a circumstance where you already know what it is before you look at it. And you turn that into, oh yeah, well that's because they're entangled, and that's, you know, they turned Einstein's right and left hand gloves thing into this wooey crap. Einstein wasn't advocating for any of that shit, and they said, well, it's a theory proposed by Einstein. No. Just such horse shit. I mean, they just lie about the past so gratuitously. You know, Schrodinger wasn't a big fan of their wave interpretation of his equation. I mean, all this stuff, they just keep propagandizing over the truth. It's the most proven theory, most accurately fantastic theory in the history of mankind. We sat and watched the roulette wheel, and we accurately, after watching 1,468 permutations, we actually predicted that there's an even amount of times it comes up all of the numbers. And we predicted it so accurately by observing what it does. Yeah. I mean, it's like me predicting that you know a duck is swimming in the water, and I watch some ducks and then they fly, and then I predict that yeah, eventually that duck that's swimming, he's going to fly. I predict it, and I have tremendous accuracy. Every single duck you point to ends up flying away. Every single one, you know, except one's eaten by sharks or something. Yeah. All right. Tremendously accurate. I mean, I can predict it to 10 zillion decimal places. I'm so good at predicting. You know, that I did this experiment where I ran 50 miles an hour into a brick wall, you know, with my head, and I predicted every time the bricks left a big impression in my brain. Every single time. My prediction was so amazing. I did the experiment a million times. I was a million times got the same answer. God, I'm brilliant, aren't I? Isn't my math perfect? Isn't my whole theory so incredible that I predicted, you know, that if you take a big metal blade and you slide it onto somebody's neck, that their head falls off? I'm amazing, aren't I? That every time I predicted that guillotine was going to cut his head off. Every fucking time. And it came out that way every fucking time. Isn't it an amazing theory? Isn't it so obvious that my God is God? Because I can predict guillotines cut people's heads off? Isn't it incredible? Aren't you convinced? I predicted so much. Shit. I mean, it is a comic routine, really. It deserves, you know, too bad George Carlin didn't know physics and couldn't have mocked this shit. Because it just deserves mockery. It's so fucking stupid. Stupid answers for stupid people. That should be like General Electric's stupid fucking propaganda for dumbass dupes. Eat your propaganda, fuckheads. God, I hate this fucking planet.